Some rational functions have a feature in their graph called a vertical asymptote. This video will be all about rational functions and their vertical asymptotes. Okay, well, let's just examine the function f of x equals 1 over x, and that's going to lead us to what a vertical asymptote is. So I just want to imagine that someone asked me to graph this function. Well, if I don't know anything else, if I'm not told anything else, the only tool I have is to plot points. But the first thing I want to realize is that the domain of this function does not include 0. I can't plug 0 in. Well, because I can't get 0 on the bottom of a fraction. So let's pick some x's and find some y's. So maybe I pick -2, -1, and I'd usually like to pick 0, but I can't because it's not in the domain. So maybe naively I just pick 1 and 2 after that. And I've left a gap in my table because I'm going to go back and plug in some values in a moment. I'll probably need even more room than that. But for now, let's just plot the points we have. Well, plugging in 2, I'd get out 1/2. Plugging in a -2, then make that a -1/2. Plug in a -1, I get out -1. Plug in a 1, I get out +1. Let's plot those points and see what's going on. At -2, I'm at -1/2. At -1, I'm at 1. At 1, I'm at 1, and at 2, I'm at 1/2. All right, well, I don't know a lot about what's going on in this graph yet, so I think I need to plot more points. So maybe between these two, I decided to plot -1/2 and +1/2. Well, y equals 1 over x. If I plug in +1/2, I get 1 over 2, which is just 2. Right? I get 1 times 2 over 1 is 2. Here I get -2, just the opposite sign. All right, so if I go to x is 1/2, I get out +2. X is -1/2, I get out -2. And all of a sudden, I'm starting to see something that looks a little bit like a shape I might understand emerge. But let's just pick some more x's. Let's pull out a 3. Well, I get out 1/3. Well, in this video, I don't really care what's going on this way, but I could imagine plugging in a -3 and getting out a -3. And I think I have a behavior going on here. We'll talk about that in one of the other videos down the road. Right now, I want to think about what's happening when I let the x's get closer and closer to 0. So let's imagine plugging in -1/3 and -1/4, +1/4 and +1/3. Well, this is a reciprocal function, right? Just like when I plugged in the 1/2, if I plug in a 1/3, I get out a 3. If I plug in I'm pointing to the wrong spot. If I put a 1/3 in there, I'll get out a 3. If I plug a 1/4 in there, I get out the reciprocal, 4. And I think I understand what's going on. At 1/3, I get out 3. And as I get closer to 0, I get out an even higher number, 4. I think my graph keeps getting taller as I go towards the y-axis. I see the same thing happening here. So I think what's going on here is as x gets close to 0, on the right, the y values get infinitely large. I'm going to erase part of my table so I can write a similar statement about what's going on the other side. As x gets close to 0, on the left, the y values get smaller and smaller. They're going towards a -infinity. So as the x values get close to 0, on this side, the y values grow without bound. On the other side, they fall without bound. That's what I mean by smaller and smaller, more and more negative. This is what we call a vertical asymptote. I have a vertical line where the y values grow or fall without bound. And this one, they grow without bound on one side and fall without bound on the other. That's what we mean when we say a vertical asymptote. Here's a definition. The line x equals a is a vertical asymptote if the y values increase or decrease without bound as the x values get close to a. From either the left or right. Didn't give myself enough room. All right, so that's what it means to have a vertical asymptote. You have y values growing or falling without bound as the x values get close to a certain value, and we get a vertical line, right? A vertical asymptote. All right, well, there's a nice way of knowing where vertical asymptotes happen in a rational function. So let f of x, our rational function, be a polynomial over a polynomial. That's in lowest terms. So when I say lowest terms, what I really mean is that p and q should share no common factors, that there's nothing that if I factored would cancel. So if I had x squared minus 1 over x plus 1, this is not in lowest terms, because I could factor the top and cancel a term out on the bottom, right? Those cancel. So that's not in lowest terms. Whereas if I had something like x minus 1 times x plus 1 all over x minus 2. Now that is in lowest terms because I can't cancel anything out. All right, so if I have a rational function in lowest terms, the vertical asymptotes occur, usually abbreviate vertical asymptotes there as a VA. So the vertical asymptotes occur at the zeros of the denominator. So if I wanted to find vertical asymptotes, for a rational function, all I have to do is, number one, hope that my rational function's in lowest terms, and then number two, set the bottom equal to 0. So I'm going to change this on top here. It's what you get when you make up a problem. You accidentally write one that wasn't in lowest terms or might not have been. So I'm just going to play it safe and change that to an x plus 4. All right, the vertical asymptotes happen at the zeros of the bottom. So let's see what happens when I set the bottom equal to 0. All right, well, that factors nicely. So I see the bottom is equal to 0 at x is 3 and x equals minus 1. Those are my vertical asymptotes. And notice when I write those down, those are equations of vertical lines. They're lines in the format of x equals 3 and x equals minus 1. A vertical asymptote is always a line, so we write it down as a line. Don't just write down numbers. You have to write down x equals 3 and x equals minus 1. Plus, it's always a good reminder that when we write down x equals 3, that's the equation of a vertical line. X equals minus 1, that's also the equation of a vertical line. So when we write down vertical asymptotes, we will always write them down as equations of lines.